So last time we talked about all the different parts making up our chemical equations and what we're actually doing with it. We're creating a new product out of different reactants, one or two things that we're adding together to make it, right? So if we look at a simple one like this one, we know that because of the law of conservation of mass, we have to have the same number of each atom on the reactant side as we do on the product side. So this is a simple one you should be familiar with because you were already technically doing this reaction when you were making ionic compounds. But we have aluminum and we have bromine going together, okay? So bromine naturally forms, usually as I'm guessing a gas, a lot of times it's a gas, with having it double up. So you're always going to have two bromine. Aluminum can be by itself as a single atom. But when it forms aluminum bromide, then you're going to need two aluminum to every 6 bromine. Now, if you have that on your product side, that means your reactant sides, we need the same amount. So if you see you had 6 bromine here and 2 aluminum, well, you would have only had 2 bromine and 1 aluminum here, so you needed these coefficients to multiply. 3 times 2 gives us the 6 over here. 2 times 1 gives us the 2 aluminum. So you have to have the same number on each side. Don't worry, we break this down into simple rules. So this is the gist of what rules we need to use. First, you write your unbalanced equation. Then you're going to count the atoms on each side. Third, you're going to add coefficients to make equal numbers. So the coefficient times the subscript is equal to the number of atoms. Notice you never ever change those subscripts. You're already dealing with a certain molecule that you're either putting in or getting out. You're not going to change that. Changing the subscript would change the molecule. You're changing the amounts you're putting in to what you're getting out. Reduces the coefficients to the lowest possible ratio if necessary. So that only applies to the coefficients. So only the large number in front, if they have a common number we can divide into, we divide across the board. But I'll show you that in a minute. And then you're going to double check the atoms to make sure they're balanced. Let's take a look at one. So let's look at my example from last time of making table salt, because I told you in its base form, it's pretty dangerous. Sodium will explode because it reacts to the air, and chlorine forms a gas, which is a Cl2, right? But it makes pretty harmless salt, table salt. And notice it's not balanced. We have more chlorine on our reactants than we do in our products. So the very first thing we do is we write our unbalanced equation. Check, I did step 1. Step 2. Now, for step 2, I'm going to go ahead and show you how it's nice to set up. Think about this as your equation, and this is your equal sign, right? And we need the same amount of each thing beforehand as we have afterwards. So I'm going to write every atom I have down here. I have sodium here, and I have chlorine here. I can see that I only have 1 sodium, so I'm just going to write a 1, but I have 2 chlorine. Then on the other side, I should have the same atoms, and so it's a good way to double check to make sure you didn't miss any out of your reactants. Yes, I have sodium, and I have chlorine, right? And if I'm counting, I only have 1 sodium on here and only 1 chlorine on this side. So that means that it's unbalanced because I have more chlorine over here than I do over here. And that's okay because we haven't done the third step, which is add our coefficients to balance. Now, to balance this, I can't add any number, because we only do coefficients of whole numbers, to chlorine to make it less. So I'm going to have to go ahead and add a coefficient to sodium on my product side. So let's do this in blue. If I add a 2 here, right, I now change all of these, so that makes that a 2 and that a 2. Chlorine's now balanced, but sodium's not. Well, I can come over here and I can also add a 2 coefficient in front of sodium, which is going to change that to 2 as well. Now I've balanced it because I have the same number of elements on each side. And that's where we would do that check. 2 sodium on this side, 2 sodium on this side, 2 chlorine on this side, 2 chlorine on this side. And you know that this is a balanced equation. The only other thing we would have needed to do is reduce. But since there's secretly a 1 right here that's in front of that chlorine, this doesn't reduce because it would be the coefficients are 2, 1, and 2. We don't write the 1 though. That's very important to remember because the reason is I wouldn't have written this molecule at all if I didn't have at least one of them. So if I wrote a 1 right there, that would just be extra redundant, wouldn't it? So now I'm saying there's one of this only one molecule that I wrote out there. That's kind of pointless in a way, so they don't bother writing that one, they just leave it blank. And it's assumed that there is a 1 in front of that. And so I can't reduce this one because 1 only goes into itself and it can't get any smaller. Okay? So that means that is indeed my final balanced equation for making table salt is 2 sodium plus a diatomic chloride atom equals 2 molecules of sodium chloride. And that's it. Here's another slightly more tricky problem that you can see that it dealt with aluminum and copper chloride, and they came together in order to make copper and aluminum chloride, and you needed to add coefficients to every one of them just to make this balance. But notice they did the same thing. They put how many they originally had. As they added their coefficients, they changed their totals here. And then they checked to make sure they have 2 aluminum on this side, 2 aluminum on this side, 3 copper on this side, 3 copper on this side, 6 chlorine on this side, because it's 3 times 2, so that's 6 chlorine here, equals 6 on this side. 2 times 3 equals 6 chlorine there. And that's how that works out.